Sandra, Kingan from Brooklyn College, CUNY, will talk about some very interesting things about matroids. Or if you'd like to join us, as usual, we are going to have dinner at 6:45 at Evelyn's. If you'd like to join us for dinner, everybody is welcome, but let me know right after the talk. Thank you.
Thanks to the organizers for inviting me to give a talk. It's a pleasure to come back here and give. The last time we gave a talk, it was over 10 years ago. So I'll start with what is a matroid. I won't assume that you know matroids. Then I'll do binary matroids, excluded minors, and then decomposition results. So. A rank 3 matroid is a set of points and subsets of points called lines such that the points and lines satisfy the usual axioms that you would expect points and lines to satisfy. So 2 points belong to exactly one line. A line contains at least 2 points. And a condition to make things non-trivial, there are at least 3 non-collinear points. To make it rank 3 points on a plane. So for example, here are 3 matroids that I will draw. 3 points on a line. So this line is not a graph. It's a geometric picture. 3 points on a line, 1 point outside. Here's another one. Our lines can be curved. And then this is the Fano that we were just talking about, right? That's the Fano matroid. This is the projective plane, and that will come in a little bit. So let me number these points. 1, 2, 3, and 4. Another way of presenting these points here, this diagram of points and lines, is with a lattice. So the empty set, points will be the first level. Right? And then the lines will be the next level up. So the lines will be 1, 2, 4, 2, 3, 3, 4, 1, 3, and then the whole set, 1, 2, 3, 4. So this is the first diagram over there. 1, 2, 3, and 4 like that. And 1, 2, 1 is where else? 1 is here, 2, 3, 2, where else? 4, 3, 3, 3, and this one. I think I've got them all. So this is the same as this. So this is what a rank 3 matroid is. All right? You can present it like this, or you can present it like that. So a rank 4 matroid, I'm just going to read it out because the axioms are long. Set of points and subsets of points called lines, and subsets of points called planes. Because in rank 3 you have planes such that these 2 points belong to exactly one line. Line contains at least 2 points. A plane contains at least 3 points. 3 points belong to exactly one plane. And then conditions on lines and planes. And a rank 5 matroid, you can have points, lines, planes, three-dimensional surfaces, all satisfying the usual properties that you would expect points and lines to satisfy. That's what a matroid is, and keep going like that. If we were expressing it in this manner, it would be very long. The axioms would grow. There's a much shorter way of expressing it, and that's what I will write over here. Let E be a set and F be a family of subsets of E such that E is in this family, the whole set. 2, if F1, F2 is in the family, F1 intersection F2 is in F. And you can sort of see how points and lines would satisfy those two axioms. And the third one kind of encapsulates everything else. There's only one more instead of a whole bunch of distinct axioms on points and lines. And 3, if F is in the family, and F1 to Fk is the set of minimal, so it's a little bit long, but it encapsulates all the other axioms. Minimal members of F that properly contain F, then F1 minus F, F2 minus F, Fk minus F, partition the space, E minus F. So this one, it's a non-trivial axiom, and if you were doing a course in matroid theory, it would actually come in about 3 weeks is when you would see this axiom. So it's not the first thing that you would present, but this would encapsulate all of the other things that we were trying to say about points, lines, and planes. And this is where I'll stop with the geometric perspective here, because I'm going to be doing only binary matroids, which are actually just 0-1 matrices. And Hassler-Whitney, matroids originated in New Jersey. That's not a joke. Hassler-Whitney was at Princeton when he wrote a paper on the abstract properties of linear dependence, and he extrapolated the main axioms that described independence in vector spaces and independence in graphs. And then shortly after that, McLean said that it was just combinatorial geometry. Combinatorial geometry now means something else. Rota actually wanted to call this combinatorial geometry, but it was sort of overruled on that, and matroids is the name that is stuck. And Birkhoff said, well, you're really just talking about a geometric lattice. So that's what we're talking about. And we're going to kind of bring it down from there to something much more tangible, and in a sense maybe a smaller set, but a set that has a lot of structure, like graphs. So this was, if I write here, can you all see, or should I just raise the board and continue writing over there? Maybe raise the board, yeah. So, I'm going to put up Whitney's axioms for linear independence. So I like to describe this matroids like hyperlink cinema. Hyperlink cinema is the genre of films where you have disparate characters with disparate storylines, and at the end they all sort of, meet So that's what this presentation will be like. We've got some stuff on points and lines and geometries, and now we're going to talk about vector spaces. So this is how Whitney started. Let E be a set and I be a family of subsets of E such that the empty set is an I. If I is an I, then every subset of I is an I. So the subsets of, think independent sets, because that's why we're using I. And if I1, I2 is an I, and I1 less than I2, then there exists a member in I2 minus I1 such that I1 union E is in I. And if you have a set system like this, then EI is a matroid in the same way that, I suppose there was a last line here that I should have said EF is a matroid. And it is not terribly difficult to show that this axiom system is equivalent to that axiom system. But this axiom system is very good to understand why vector spaces and matrices over finite fields are matroids. So
these two definitions are equivalent?
Equivalent, yeah. There's 13 cryptomorphic definitions and many more variants.
I'm just curious, is it the case that any one of these abstract matroids can be realized concretely in terms of a vector space and affine hyperplanes, etc.?
No. If you think about the class of, it's like this. So you have graphs. This is the smallest class. Maybe I guess planar graphs would be the smallest class. And you have binary matroids. So that would be matrices over finite field, vector spaces. And then you have all the finite fields. The class of matroids is extremely large. And most of the matroids are not representable. It's just that then you lose a lot of structure. And as long as you're in the realm of finite matrices over finite fields, you have structure. So, all right, so EI is a matroid. So the example to keep in mind over here with this axiom system is vector space, right? Vector spaces rank R over a finite field or real numbers or complex numbers or any field, all right? So F is a field. And think of a matrix. Let's do binary since we'll be talking about binary matrices. So you have a binary matrix here, some matrix of zeros and ones. Let's label the columns 1, 2, 3, 4, 5, 6, 7. This matrix has independent sets, so of columns. So just think of the column labels like 1, 2, 3, 4 is an independent set. And that's what we're really talking about here. The independent sets in matrices satisfy these axioms. So if a set is independent, then every subset of the set is independent. Right? So that's just something that is done in linear algebra 1 when you're teaching matrices over reals. But the only field down there is reals. And the difference is that we'll be talking finite fields. And the third one is, it looks, involved written like this. But the basic idea is if you have an independent set, you can grow it to a basis. That's all it is. And if you were doing the proof of singular value decomposition, at some point you would need this. So it's the proof of Y vector space would satisfy that is just about this big, about 3-4 lines, and that's considered the first proof of matroid theory. It's a proof that vector spaces satisfy this. So, a set that is not independent is called dependent, right? And a minimally dependent set is called a circuit. So the circuits also have their own axioms. And I'm going to quickly put up the circuit axioms because that's the best way to understand why a graph is also a matroid. So I'm actually talking about a class of objects that sort of contain the graphs in them. So the first thing is a set, and C is a family of subsets. Instead of EI, you have EC. And the circuit axioms are, and as I write these down, just think of cycles in a graph. In matroids, we call the cycles in a graph circuits, just to be confusing. Okay. If C is a circuit, then no proper subset of C is a circuit, right? Is in C. So if you have a cycle in the graph, no proper subset of that will be a cycle. And 3, if C1, C2 are cycles, and E belongs to C1 intersection C2, then there exists a third cycle contained in C1 union C2 minus E. So you have, now we're thinking graphs, okay? You have a graph, you have a cycle, you have another cycle, they have a common edge E. You remove E, you'll find a cycle in what's left. This axiom system equivalent to this axiom system, equivalent to that axiom system, and there's 13 of this, but I'll stop over here. Actually, in the first page of Whitney's paper, he defines a matroid as a function, a discrete function that satisfies certain properties. So, and that's not what I will present over here. So with this introduction to matroids, let me start talking about binary matroids. Just give me the time.
So binary is rank 2?
Right. Field 2.
Oh, field 2.
Field.
Oh,
Yeah.
GF2.
Yeah, GF2. So I will erase this. And I'll just stay on this side of the board so you don't have to turn the camera all the way there. Okay. I'm going to have a graph here, and I'm going to label the edges E1, E2, E3, E4, E5, and E6. All right? Edges. Don't care about the vertices. And I'm going to write the incidence matrix just to speed things up a little. Copy this. For the incidence matrix, it would make sense to actually start out by labeling the vertices, right? Because we have with a little effort, we can do row operations, elementary row operations on this matrix, and write it in standard form with the identity on one side, and you would get actually this. So do what it takes to get rid of, to make some of these columns identity. So there we go. So this row is unnecessary, right? So elementary row operations will get you this, and we can write this as I4 like this. This is how we think of graphs in matroids. So it's a variation on the incidence matrix. And we don't do this to get that matrix. You can get it directly. So E1, E2, E3, E4 is a basis, is a spanning tree, right? E5 is a cycle with E1, E2, E3, E4, right? It's a cycle. And this is a dependent set here over the binary field, F2. Right? 1, 2, 3, 4, 5 is a dependent set. And same for the other one. So you can get that directly. And that's how we think of a graph in matroid theory. And what is a binary matroid? It's just any 0-1 matrix. Right? So we started off with all these axiom systems, but then we made it extremely concrete. It's just, I'm talking about the class of 0-1 matrices, and that's what I'll be talking about for the rest of this talk. So a graph is a special kind of 0-1 matrix. A binary matroid is any kind, any 0-1 matrix. That's it. So after all the axiom systems, we come down here. And we will not have any repeated columns. We won't have the 0 vector either. And such matrices we'll call simple, because actually the 0 vector corresponds to a loop, and repeated columns will correspond sort of to parallel edges. And simple binary matroids, and if you replace matroid by matrix, it would be perfectly fine. Okay. Will sit inside the projective geometry. That's the whole space if it's rank 3. So projective geometry, the notation is PGR minus 1, and you put the order of the field here, which is 2. So it's always 1 off. So if it's VR 3, 2 for the vector space of rank 3, it'll be PG 2, 2. And that's actually the Fano matroid that I put up earlier. That's a projective plane. And this is PG 3, 2. And now the computational aspect is starting to come into focus. When you lose a picture, you kind of lost something, but you got a matrix, so it makes it easy to do computation. So this would be 0, 1, 1, 0, and all of them up to 15. So this would be PG 3, 2, and then PG 4, 2, etc. Right? So people who study graphs are studying objects that sit inside the complete graph, right? You have the complete graph on 5 edges, for example. And any rank 4 graph, spanning tree is 4, would sit inside this. I study objects that sit inside this. Now, the largest KR, we use R plus 1 because it's KN, the size of the complete graph is n choose 2. The size over here is 2 to the r minus 1. So we're working with exponentially larger objects, but it's astonishing how similar they behave to graphs. In fact, just very simply, any result that is just on edges in graphs is most of them transfer to binary matroids, 0-1 matrices. So exponentially larger, but still behaving just like graphs. So
the analogs for many graph theory statements to matroids?
yes, any statement with edges, just about edges, not vertices, because we kind of lost the vertices when we did this, is very likely to transfer to graphs. And if there's a statement that doesn't transfer to graphs, that's also news.
Yeah.
Yeah. So, and the transference is not necessarily sort of, exactly the same. It's a larger class, so it's a little bit slightly different result, but it's very likely to hold without too much extra stuff. Okay. So section 3, excluded minor results. And while I pause, you can actually look at Rota's quote over there, because that's what he's saying, is that you have all these things from vastly different pedigrees, and they're all talking about the same object. So now I'm going to just do graphs.